So, I do get that binomial formula crazy thing is definitely really hard. We'll do another example today at the end. But we're going to shift a little bit and talk about continuous random variables. So everybody should have gotten one of these little, tapping at the end, okay? Everybody should have got one of these little sheet things. Did you guys get one of these that has a front? Yours has a front and a back because it's two-sided. Yes, you got it? Yeah, it says standard number probabilities for z less than 0, right, on one side, and then it says z bigger than 0 on the other side. So we're going to use that today in class. Hold on to this, and you're going to need it on tests and stuff. So just try to, not lose it. I'll have extras and things as well, but it's helpful for them to make copies of the same thing repeatedly, okay? All right. So what is a continuous random variable is one for which the outcome can be any value in an interval or a collection of intervals. So, wow, that was fun. This is even more fun. It's like a party on my iPad. Woo! Okay, sorry.
Stay on topic.
Anyhow, that's a continuous random variable. Well, the other ones we were talking about before, those were discrete variables, right? Where only whole number values were possible. So for those whole number value things, you had tables, and the stuff in the table had to add up to 1. Does that make sense? For continuous things, you're going to have functions. So this is called a probability density function, and it's a curve such that the area under the curve over the interval of all interval is the probability that x is in that interval. So here is an example. Okay, we'll draw a common situation is that you have a bell-shaped curve. So let's just draw a approximately bell-shaped curve. That middle value ends up being your mean. So first of all, let's start from this a little bit backwards. The area under the curve for the entire range of possible values must equal 1. That's kind of similar to the probabilities in your table has to add up to 1. Does that idea make sense? So the area under the curve encompasses all possible values, and therefore that area must be 1. If you want to find the chance that some number x is in between a random a and b, so that's your a, that's your b, the probability that x is in between a and b is the area under the curve. And I know it might have been a long time since some of you guys had algebra, but that inequality is the way you write in between. The lowest number goes first, and the alligators eat towards the bigger number. Does that make sense? Not to treat you like fourth graders, but.
Put teeth on it, it'll make more sense.
Yeah. So if the total area has to be 1, what is true about the area between any a and b? What does it be less than or equal to 1? And you have actually kind of seen this already because we had that whole 68, 95, and the number I can't say without stuttering rule. Yeah? And so what that rule was telling you is that if you went from your mean and then, was it minus a standard deviation? So minus mu minus a standard deviation and mu plus a standard deviation, what percent of things lived in that middle part? 68. So what that would be as an area would be, the area is 0.68. Does that make sense? And if you go 2 standard deviations away, the area under that curve is 0.95, right? 3 away, it's 0.997, yes? So you kind of already seen this. And technically, to find areas under curves, once your curves get more complicated like this, I would suspect that most of you don't know how to do that, unless you've had calculus 2. Because this reduces to something called an integral, which finds areas under curves. And the normal curve that does bell-shaped data for things that are commonly normally distributed, to find the area under that curve, even my calculus 2 students can't do it because it's too complicated. It requires graduate level math to work out what that thing is. That's why you have that table. That table that you have tells you area under bell-shaped curves between different standard deviations away from something. So notice how all the numbers are all less than or equal to 1, right? So their areas under curves, and that little picture it's giving you tells you that it finds the area from some value to the left of it. So we're going to start with the simplest possible thing, and the simplest possible curve is called a uniform random variable, where instead of being a curvy curve, the curve is a straight line. Okay, so here's an example of that. So a probability density function that is a flat line that covers all possible values for x. If the range is from a to b, then the base is b minus a, and its height is fill in the blank. Okay, so the point is from some a to some b, your function or your curve is just a horizontal flat line. The uniform means it doesn't change, as in doesn't go up, doesn't go down. Okay. And we don't know how tall it is yet, but we're going to figure it out. So what must the area equal? Because it's a probability thing. And if A and B are like, from A to B is all the possible values, what's the area got to be? It's a probability curve, the area and it has to equal 1. So the area's got to equal 1. And this is a rectangle, right? So how far is it from A to B? Like pretend like B was 7 and A was 2. That's 5 units. So 7 minus 2, this is B minus A. Does that make sense? Okay, so if I have that area is length times width, has to equal 1. If my length is B minus A times W equals 1, can you solve that for W?
Yes.
Yeah, so what's W got to equal? 1 over B minus A. Exactly. So the height of this curve is 1 over B minus A. So in the example of my 2 and 7, the base is 5, what's the height got to be? If this were 5, right? This needs to be 1/5. Because 5 times 1/5 gives you 1, right? Okay. What if my base had been 10? That might be 1/10, right? Okay. So we won't have many examples of that, but the point is this is a curve that you can actually find the area underneath, as opposed to other stuff where you have to use tables and things. So suppose you have a uniform random variable and x is between 0 and 10. So let's start by sketching a picture. So our x's range from 0 to 10. And this is going to be not drawn to scale. Because they said it's uniform, that means I've got this whole flat line thing going on. So how big is the base of that rectangle? 10. Since its area must be 1, the height has to be 1/10. And don't worry about drawing stuff to scale, just like label your points. Does that make sense? Okay. So we're going to suppose that this curve tells us wait times for buses are between 0 and 10 minutes. So like this is x, which is your wait time. And this is the area under the curve interpretation is the reason that you can't find probabilities for an exact event. Like the area under a curve for a straight, just a line would be 0. Like lines have no area. Does that make sense? But what about the probability that x is between 0 and 3? I'm sorry, 0 less than or equal to x less than or equal to 3. What does that mean in the context of like waiting for this bus?
It could take you up to 3 minutes.
It takes you some time between no minutes and 3 minutes for your bus to arrive. That's what this is telling us. And that is the area under the curve from 0 up to 3. So that is the probability that we're looking for is the area under that curve. Like that's what this is. So what is the chances you're going to wait between 0 and 3 minutes then?
0.3.
Yes, it'd be 3 times a tenth, because that curve underneath it's a rectangle, right? And 3 times a tenth is 3/10 or 0.3, right? 3 times, how do fractions multiply? Just like, quick review. Multiply like across, like top times top, bottom times bottom. So that's 3/10 or 0.3. Or a 30% chance you'll wait between 0 and 3 minutes. But the point is, for continuous function, the probability is an area under the curve. That's the main point of this. So sketch your curve, find your area. How about 4 and 5? So we're looking for probability that 4 less than or equal to x less than or equal to 5. So that's the chances your wait time is between 4 and 5 minutes, right? So is the picture of the curve without the shaded part going to change? Okay, so that first part's going to stay at a height of 1/10 up to 10, but you care about from 4 to 5, right? That's the area you're looking at, which is also rectangle, right? Its base is 1. What's its height? 1/10. So 0.1. That's the probability you wait between 4 and 5 minutes. Does that make sense? Okay, and how about the last bit? What's the chances your weight's going to be greater than 5? So there's 10, height still 1/10, but you shade the curve from halfway on up. So probability x is bigger than 5 is going to be 0.5. 5 times a tenth, which is a half, or 0.5.
Wait.
Yeah. Go ahead.
Yeah.
I think I know what you're going to
not
ask.
Equals.
That's a great question, because I was going to just go there. So I did say greater, and technically speaking, greater doesn't include equals to, right? Like technically speaking. But if I added in the equals to, would that change the probability? It wouldn't, because the area under on a line is 0. So if these continuous variables having an equal to or not will not change your answer. Because what this finds is just the area from just 5 up. You see what I'm saying? Because adding that specific 5 in has area 0, so it doesn't change the area. Does that make sense?
Yes.
So it's the fact that an area of a single line is nothing. So yeah, in this case, the or equal to you can be really messy and it doesn't matter. But with discrete variables, it matters a lot. Because it's like, oh, did you include 2 or not include 2? And that changes the probability a ton. So yeah, it's a great question and doesn't matter. So I won't be picky about it either with stuff like this, since it's like not that important. So if you'd put an or equal to there, whatever, I don't care. Okay, so what this function assumes when you draw like a straight line like this is it assumes that all wait times are equally likely. That's what this says. It says, okay, waiting 0 minutes is just as likely as waiting for 5. And do you think that's probably true? In general, that's not true, right? So in general, that's why these are just an example of stuff where you think, okay, probability is area for continuous functions, but in most situations in real life, you have functions that actually have a curve to them, and you've got the question of how do you find areas under curves. That's the big idea. So the big category we're going to talk about a lot, and almost pretty much like for the rest of the semester, is something called a normal random variable. So this is something that has a bell-shaped probability density curve called a normal curve, so like that curve that I sketched earlier. And it's completely characterized, I'm sorry, I can't English. This should say characterized. I don't know why, I can't get my tenses right. By specifying values for its mean, which is called Greek letter mu, and its standard deviation. What was the Greek letter for standard deviation? Do you remember? It's called sigma, yes, and somebody drew it in the air. It's totally, that's a circle with like a line off one of the ends.
One of the ends of the circle.
I just can't, the right side. Yes, sorry. Okay. And these are the curves, and when you look at one of these curves, where's the mean gonna be? In the middle with all the big part of bell-shaped. The normal curve is symmetric and bell-shaped. This is kind of a technicality, but every symmetric bell-shaped curve isn't necessarily normal. And actually, now that I've taken some more statistics, I know of an example of that because we did one in my class. But in general, if you have a normal curve, you're going to be symmetric and bell-shaped. Okay, this must be pretty intuitive. Okay, your mean is your middle value, right? What's the chances, or what's the area under the curve to the left of the mean and to the right of the mean? Well, just like one at a time. So the area to the left has to be 0.5. The area to the right has to be 0.5. The mean divides that area of 1 into halves, right? Okay, so should say 0.5. So this means that the probability that a measurement is less than the mean is equal to the chances that it's greater than the mean. Okay, is that part all right? All right. So this next one, it looks a little bit funky. You got this like mu minus d and this mu plus d, and you're like, holy patootie, what does that mean? So let's draw a picture of that. So we have a normal curve, and it has this bell-shaped, and that line I drew is the mean. So pretend that I could draw something symmetric, okay? I'm super sorry that I suck at art.
Reminds why you're not an art teacher.
Mu plus some d, so assume some d is a positive number. Yeah. So if mu plus d is a little bit over here, it's like d units away, how many units away is mu minus d from mu?
Same.
The same, just in the opposite direction, right? So over here, that's mu minus d, right? So one of these is the probability that x is less than or equal to mu minus d. Which part of the curve would have the area under that corresponding to that probability? The left side or the right side? The left side. So that is represented by whatever this area is. Does that make sense? So the area under the curve here tells you the chances that your x is less than that value. Do you agree? And which part of this is probability your x value is bigger than that mean plus d? The other end, right? This stuff over here, right? Because of symmetry, how would the number you got out from the purple thing on the left relate to the number you got from the purple thing on the right? They're going to be the same. Yep, it's going to be equal. I think I just like totally English that bad. Whatever, okay. Did I fix yours? Yours probably is not as stupid as mine. Whatever, okay. Oh, I'm looking at the wrong part of my notes. Okay, so this means probably that x is more than d units that's above the mean. You see that's d units above. Equals probability that x is more than d units below the mean.
When you go for a coffee run?
Always. Okay, and then one last thing, and we'll do some actual probabilities, almost. This is the empirical rule. So mu plus or minus 1 standard deviation, what should the area under the curve be approximately? 0.68, 68%. And see how that's 1 standard deviation above and 1 below, right? Just using that sigma thing for standard deviation. How about for 2 standard deviations? 0.95. And then how about for 3? 0.997. And actually, like now that we are going to know a little bit more, you can actually compute that these 68, all these numbers are definitely estimates. Like it's always a little teensy bit off from what it actually is, but it's good enough for an estimation. Okay. And some other useful rules. So that table you have here, notice that like that fancy curve, it's shaded to the left, right? So this table always finds areas from the number you have to the left of it. So if your number isn't to the left, you've got to make it into a left. Does that make sense?
No.
Okay, so let's look at this one. Suppose I wanted to find this area, okay? But my table will only go and give me that area.
Well,
See,
don't you take that and minus it?
it's the complement thing. Does that make sense? So the probability that x is bigger than a is 1 minus the chances that it's less than a. Does that make sense? And then this business thing, that thing you can find in your table, assuming you have a normal curve and a specific value. You got a little bit of pre-processing first before you do there, but it's the complement rule again, right?
The little symbol at the bottom is an A, right?
Say that again?
The little tiny.
That's an A. Yeah, I scanned it out of your book and it's not awesome, but yeah, that is the letter A, definitely. Okay, is everyone okay with that one? Okay, this next one, the probability that x is between A and B in terms of areas. So let's draw it in two colors. So if I shade that part, that's the probability that x is less than or equal to B, right? Remember, the or equal to's don't really matter that much. I left the equal to on or whatever. So is that the probability that I'm after? No, it has extra junk in it, doesn't it? So I have to take away
Probability that x is A.
probability that x is less than or equal to A. Now, one thing that kind of freaks students out a teensy bit with stuff like this, do you see that there's actually a little bit of inequality flipping that happens here? I don't know if it's good to point that out or not, but you see how there is like a little bit of flippage from the original relationship? But I think if you just think about it in terms of areas, well, I can find the area from B down and take away the area from A down. That's why this is the rule. It's because of, I want this area in the middle, and I find up to the highest point, and then take away up to the lowest point, and that gives me the middle. So it's just area subtraction. And this final one, if I was looking for this value, I could instead find
The other side?
the other side.
So you just flip it or so?
Yeah, because of the whole symmetry thing, those two things are equal, right? Yeah. Okay. So, we're going to actually get to that table almost. Any questions about the areas?
Why can it be less than or equal to?
Oh, because the or and I should really be consistent. Let me just take that equal to off, but it's true without it even. The reason is because when you add in the or equal to, all you add in is the line that includes that number.
Oh, it does.
And that has area 0. That's the exact same question somebody else asked, but it's exactly.
Okay.
Totally fine though. Yep, makes sense. Okay. So we talked about things that were bell-shaped, normal distributions, when we had like weights of people and heights of people and stuff. And depending on the context, you're going to have a different value for your mean and a different standard deviation. Does that make sense? There's a large standard deviation in height relative to like handspan. Does that make sense? Like our handspans aren't going to vary that much, but our heights are going to vary a lot more, right? And they're also going to have different means, right? So you need a way to kind of make them all a standard, and you use that Z thing. Remember this Z-score thing we did earlier? So you use that standard thing to change it into a standardized value that describes how many standard deviations away you are. Remember, Z equals 1 means you're 1 standard deviation above. Z equals -1 means you're 1 below. Z is -2.5 means you're 2.5 below. If your Z is -0.6, like Martha Stewart, are you special? No. No? Okay, Martha Stewart's not special? Okay, great. Okay, so for a standard normal random variable. It has mean, mu equals. So when you do this whole standardizing, if you do the whole z thing, what does the mean become? 0. Does that make sense? You are think about this as standard deviations away. If you are the mean, you're no standard deviations away. Right? And the standard deviation now becomes 1. That's what doing the whole normalizing thing does. And it tells you how far you are from the mean in terms of units of standard deviation. So then we can tell, like, okay, how special is your hands and how special is your height? And we can compare, like, are they both special or are your hands really small relative to your height? And then nothing about that comment. Sorry. This is just too much. And so here you go. So then once you do this whole z thing, that's what this table is telling you. Like the negative 3.4 is 3.4 standard deviations below the mean. Negative 1 is 1 standard deviation below the mean. That's what this table is saying. So go to this table, like look at the first page has z less than 0. And look at the negative 0.0, like the bottom left column that says 0.5. And lots of zeros. You see that that's actually the mean?
Yeah.
And so the chances that you're at the mean or less are 0.5, which should make sense, right? Okay, we'll talk about how to read this in just a second, but that's just an introduction. Okay, and then we're going to have to find these z-scores, and the way you find them is you use your value, which is like you're given a specific x or something, minus your mean over your standard deviation in symbols for your note card and shortcut, x minus mu over sigma. And that's going to give you a z value to look at, a standardized value. So let's just find some standardized values. So mu is 10, sigma is 6, and x is 4. So z is equal to x minus mu over sigma. I think it's negative 1. 6 minus 10 over 4. Z is equal to?
Wait.
No.
You have those all over the place.
Yeah, no, those aren't.
It'd be 4 minus 10.
4 minus.
Oh my God, what is wrong with me? Apparently I do need a coffee break, yeah. So x is 4, mu is 10, sigma is 6. Then we get negative 1. Thanks, guys. Sorry. Ugh. So that measurement of 4 is 1 standard deviation below the average, right? Okay. How about if mu is 1, sigma is 1, and x is 1? 0. So it would technically be this one minus that one, not that it matters at all, right?
So if all of them are the same, it would always be.
And that's not even required. As long as your x equals your mu,
True.
it doesn't matter what your sigma is, right?
Yeah.
As long as you'll have 0 in the numerator and 0 divided by something is 0.
Yeah.
By any number other than 0 is 0. Okay, so that person, they are totally, completely average, right?
That's hot.
Yeah.
That is how you hurt somebody.
I'm so sorry, guys. You're average.
Totally
Also known
average.
as basic.
One more thing. Here's my.
Spice latte.
Your pumpkin spice latte. Just because dyslexia happens, do you understand my analogy there? I think it's a great analogy. The O is like a 0.
Oh.
It's okay to have a 0 in the top, but it's not to have it in the bottom. It's not, okay, maybe no one's impressed by this, but
That's great.
anyhow, because I'll get students that say 0 over 1 and they say undefined. Does that make sense? Like it's just because you don't think about, okay, 0 divided by 1 means how many 1s in 0? There are none, right? But 1 divided by 0 means how many zeros in 1? Well, God knows I could add 0 forever and never get to 1.
Yeah.
Does that make sense? Because it's having to flip to understand that's the problem, but there's a little... Okay, moving on. Back to the statistics at hand. Okay, so for each value of z star, so that z star just means a specific z value, find the probability that some value you get is less than or equal to that number. So probability that z is less than or equal to 0. And so I'd like to also see like little pictures here, so I left you some space. So you have this bell-shaped curve. The mean is equal to what? 0, because it's been standardized. And actually, this one you can do without your table. What's the chances that some random value is less than 0 is the area under that curve.
0.5.
From 0 to the left, and that's 0.5. Okay. How about the probability that z is less than or equal to 0.35? Okay. So let's what? Hold on a second, okay? So first of all, in this picture, if I were to draw this picture again, where would the 0.35 fall relative to the mean? To the left or the right of it?
Right.
To the right of it. Okay, so that'd be right here, approximately. So you're looking for this area. And since the middle thing divides it in half, you know you should get an answer that's bigger than 1/2. Does that make sense?
Yes.
Okay. All right, so ready for the table. So the front page does negative z's. The back page does positive z's, okay? Turn to the back page. How this table works. The left column that says z does the whole number and the tenths place. So our z is whole number 0, and then the tenths is a 3. So go in the table until you see 0.3. That would be the fourth one down, right? And then how do you think you get the 0.05? You go over until the column says 0.05. And it might be useful to have like a note card to kind of like, so you can keep track of where you are. But you should get 0.6368. So over from 0.3, down from 0.05 gives you the area under the curve to the left of 0.35. Did you find the 0.6368?
Yeah.
Okay, so that should be 0.6368. And then just use a little bit of like, does that make sense? I think it does, right? Because it's more than 1/2. Okay. So how do you think that's going to change for when you have a negative number?
What do you mean the opposite?
Just use the opposite side. It's not quite, actually I think it is going to be the opposite as well, because that would be like the area from here down, which would equal this. So it also would be 1 minus this number, that's right?
Yeah, that's right.
Yep, that's what you meant, the complement. Yep, totally get it. I'm just going to draw a picture of where it falls though. So this is like, approximately there down. And if you're using the table just to practice it, because it wouldn't hurt. So in this case, the negative 0.3 is kind of close to the bottom. I see 0.3632. You can also make software do this for you, but we're just not going to go there quite yet. And on your test, you have to use a table, because I'm not going to use computers, because you can Google things. That's a reasonable reason, right? No, not at all. Okay. So is everyone okay with how once you have z-scores, you find these things from table? Okay. Is that all right? All right, let's now the other step you have to do is kind of like, you've got to pre-process your data to make it into z-scores, and then you go to your table. So this next one, it's a specific thing for like an actual real situation. So we have weights of college men in a specific age group. They are normally distributed, and they have mean 180 and standard deviation 20. Find the following probabilities. So our table doesn't do 200, does it? It does z values. You've got to make this 200 is an x value. You got to make it into a z value, using the fact that z is equal to x minus mu over sigma, right? So z will equal, in this case, x, which is minus mu, which is 180 over 20.
1. So z is 1.
So z is 1. So this is kind of like your work.
Isn't that the same way we used to find the z-score? Like,
Yeah, it's the exact, yes, nothing is the exact, you find the z-score, and then you use that z-score to get a probability. So nothing is different about the z-score finding, you're totally right. So that probability that you had is equal to the probability that z is less than or equal to 1. And then just go on your table and find the value for 1. So as I got 0.8413. Do you see that as well? Is anybody a little bit bothered that's not 0.68? It bothered me at first, but maybe you guys are smarter than I am, which is totally possible. So why is it not, because it is 1 standard deviation away, right?
Yeah.
But it finds the area from that 1 standard deviation away all the way down to the end, whereas the 0.68 cuts it off at 1 standard deviation below. Does that make sense? That's why this is not just 0.68. Okay? Let's standardize the 165. So z is equal to 165 is right, minus 180 over 20. And then tell me what you get. Positive or negative?
Negative.
Definitely negative, because
Negative.
you also can think, is this person above or below weight? But definitely below, so it should be negative, right? So negative 3/4 or negative 0.75. Okay, so our probability is equal to the probability that z is less than or equal to negative 0.75. So look at your table. Nah. Negative 0.75? What'd you say, sorry?
0.226.
0.2266 is what I see. Do you guys agree? Everybody else? 2266. Okay. And that should make sense because we found that if you were at -1 back in like 2nd chapter, that 16% is below you, right? Because you have 32 on either side, so 16 on the bottom half, so that's a little bit more than 16, but you're not a whole standard deviation away yet. Okay, C is related to B.
1 minus 0.2.
This is 1 minus the probability that x is less than or equal to 165, which is 1 minus 0.2266, or 7734. And I think to know you have to complement, it might be helpful to, for yourself, just like, say I'm at 165, and if I'm bigger, I'm looking for this side, therefore I must complement. And your book is often helpful like this, is they'll give you something in part B that you can use for part C. Does that make sense? We didn't have to redo the whole z-score thing because we had the z-score for 165. So, okay. I'm thinking about rainfall because we've had no precipitation and no snow sad. I really want snow too. Suppose the yearly rainfall totals for a city in Northern California follow a normal distribution with a mean of 18 inches and a standard deviation of 6. So for a randomly selected year, what's the chances that total rainfall will be in each of the following intervals? So greater than 30 inches. So first translate that into a statement with a P in it. So P, and just give it a variable, whatever, X.
No, not equal, greater.
Bigger than or equal to 30. Great.
Or equal to?
It doesn't actually matter, right? So I'm just gonna, whatever with the equal to is, won't be picky about it because no one cares. All right. Well. So you could find the z value if you wanted to, but I think at this stage you should have in your head a picture that, well, I'm like 30 on up and my table doesn't do on up, right? So I think the next thing you should do is change this into everything on down. So complementing again, right?
Yeah.
So this is 1 minus P of what? X is less than we, the or equal to doesn't matter, okay? Like, you put it there, you don't put it there, it doesn't matter. Does the complementing make sense?
Yeah.
Okay. So then we'll just work on finding this part and try to not forget to do the 1 minus that number, okay? So the probability that x is less than or equal to 30, well, we have to do the whole 30 first.
Oh, the
Do
30
like
minus.
30 minus.
Gotta do the z thing, right? Yep. So z is x minus mu over sigma. So that's 30 minus 18 over 6. Great.
Which is 2.
2 standard deviation.
So that's probability. And now when you do that, you change your x into a z. Does that make sense? So it's always, I think, a good rule of thumb to use x's for whatever your original variable is and just use z for once you've standardized. Okay, so go to your table, look for the 2.0.
0.0228.
I got 0.9772.
Oh, wait, I'm on the wrong.
You're on the negative side, probably, right? 0.9772 is what I got.
So subtract that.
So then px bigger than or equal to 30 is 1 minus that number, right? Which works out to be, oh my God, arithmetic in front of people,
0.328. 0.0328.
0.228. That whole like borrowing and carrying stuff.
In your head is not easy.
In your head is, I honestly, I can't do it very well either, so like it's, calculators, you guys get calculators in this class. What's going on?
Oh no, a bunch
There's
of
a little wind tunnel,
I thought
okay.
it was birds.
Yeah, the wind.
Okay, all right, sorry, distracted by things.
I
Is
know,
that-
it's like-
So is that part all right?
Yeah.
Okay. Alrighty. This next one's a little bit longer, but basic idea, between 15 and 21. So translate, quit watching the birds, okay, back to the class. Translate this into a P, and if I have X's between, how do you write that?
P was 15 less than, greater than, yeah.
Less than or equal to 20.
Less than or equal to 20.
There you go, okay, great. Is that all right?
Yep.
Okay. Now we translate that into probability X is less than or equal to 21. And then what comes next? Minus. Yep, exactly. And you can think about that as this is your curve and you care about, that stuff in the middle there. So 21 down minus 15 down. And then you have to find each of those other two, which means you've got to find how many z values? 2. So let's call them like z sub 1 and z sub 2. So z1 is 21 minus 18 over 6, which is negative 1/2. Do you guys agree? Negative 0.5? Okay. And yeah, I was just testing you. And the other z is negative 0.5. It's 15 minus 18 over 6, which is, that one's negative 0.5, right? I just did it another way on my notes is all, so. Okay, so there's your work. And the original probability is equal to probability that Z1 is less than or equal to 1/2 minus the probability that Z2 is less than or equal to negative 0.5. And I don't have space on my slides to do this, but if you could kind of like keep your Z calculations like off to the side, does that make sense? Just to keep it a little bit organized and keep your probabilities kind of in line, that'd be nice. Because things can kind of like mix up together and it can be hard to grade. I just don't have space to do that here. So find the first one. So look at your table, look at the positive side. What's the less than 0.5? 69.15, great. And the other side, find negative 0.5. You beat me to it. 0.3085. And that works out to be, good job. Is that okay? It's easier than binomial stuff, isn't it? I think so too. No? Maybe? Yeah, okay. Is it easier than chapter 7?
Yeah.
It's more formulaic, right? Like there's
Yeah.
steps and it gets you there as opposed to like having to like be clever and think about things. Is that a fair assumption? Right?
We don't want to be clever.
Well, but but probability, they're all different. I can't give you a formula that says do it this way and this always works, right? It's every situation's a teensy bit different from the next, right? But this is pretty sort of like plug, chug, cut and dry kind of thing, yeah. Okay, so similar idea. Heights for college women are distributed normally with mean 65 and standard deviation 2.7. Find the proportion of college women whose heights fall into this range. So 60 and 70. So P 60 less than or equal to X less than or equal to 70. And then we use the same rule as we did for part B of example 5, right? So probability X is less than or equal to 70 minus probability that X is less than or equal to 60, right? Okay. Now on the side, you want to work out our Z values. So Z1 is 70 minus 65 over 2.7. And your Z table only uses like a tenths and a hundredths, so just like use those two places. So I got positive 1.85 for this guy. Anybody else have a calculator? Yeah, got that? Okay, great.
Do you round?
Yes, so if that was like 1.849, definitely round. Yep. Z2 would be 60 minus 65 over 2.7, which I'm pretty sure comes out to be negative 1.85. And because, 1 is 5 over 2.7 and 1 is negative 5 over 2.7. That's not always going to happen on these problems. It just happened the ones I picked had that property. So probability that Z is less than or equal to 1.85 minus P Z less than or equal to negative 1.85. Okay. So back to your table. Ta-ta. 1.85. 0.9678. That sounds like a fun rhyme. And then the negative side. 0.322. Oh, FYI, this table did come from your textbook, so if you lose it, that's where it is. I'll also probably post it in Blackboard because it'd be useful to have it there in case you lose it, and I cannot be responsible for printing out copies of it. So I got 0.9356. Now let's think about this for just a moment. Does that make sense and why? So we're between 1.85 standard deviations above and 1.85 below. 1.85 is awfully close to what whole number? 2. And what proportion of numbers were within plus or minus 2 standard deviations? About 95%. You see how that's awfully close to 95? Just a little bit under, as it should be, because I have not quite as many standard deviations as 2, right? Okay, so you can use that empirical to kind of check, does this make sense? Okay, so this one, less than 60. Or X bigger than 70. And I'll show you 2 things for this. This problem is related to A, but if it were not, I also want you to know how to handle it. So you had that rule for ORs that you can break ORs into adding probably the first event plus the second if the events are mutually exclusive. As in, this is equal to PX less than 60 plus PX bigger than 70. And how do you know that these events are exclusive? Can you be shorter than 60 and bigger than 70 at the same time? No, you can't, right? If you're not mutually exclusive, it's the rule that says P of A or B is P of A plus P of B minus P, A, and B. Does that rule ring a bell? You had to use it on some homework, some quiz problems you were supposed to do. But if you're mutually exclusive, what happens to this P of A and B? It's 0, right? Because you can't be both at the same time. Okay, so if you had to, you could break ORs up like this as long as they're mutually exclusive. But if you look at part A,
Wouldn't it just be 1 minus that?
yeah, part A was looking at like you're between negative 1.85 below and 1.85, well, let's not use those, let's use the real numbers. Part A was that you were between 60 and 70, right? Like in the middle. What is this one finding?
The opposite.
The opposite end. So this really is 1 minus the answer to A. But if you didn't have it as a part of a two-part problem, you could go from here and then use your z tables, right? So that was my point. So 1 minus A's answer gives us 0.0644, exactly. Okay, awesome. So you think you can handle stuff that has to do with z's and tables and things and flippage? Okay. Example 7, this is I made your copies and I didn't modify yours. So you have to scribble out a little bit of what I wrote there and kind of copy down a little bit of what I wrote here, okay? Because I made copies and then I changed my question because I already did that question with you guys. Do you see what I'm saying? So scribble it out. It's a little different. This is a binomial thing. So just sort of summarize. There's a treatment for some hypothetical disease. And if you apply this treatment to a random patient, the chances they recover is 0.8. So like write the relevant information down on your notes for that so you'll know what we were doing in this problem. And my notes online have the stuff scribbled out and this like filled in as well, okay? So. Okay, so first of all, this is a discrete variable because, so we have X is the number of patients who recover out of how many? 4. Okay, so X could be COULD. What numbers could X be? 0. X could be 0, 1, 2, 3, or 4, right? Either no one recovers, one person recovers, 2, 3, or 4 recover. Is that okay? What's wrong?
No, nothing.
Is it the problem or is it the?
Yeah, I can't like.
Can't process it?
Reading around the other problem, no.
Can you just scribble it out and then like just,
Write that whole thing?
just, no, not write the whole thing, but just like do the work and then go back and change it after? Will that work? I'm sorry, it happened.
I'm gonna go now.
No, don't go, no, it's okay. So X could be 0, 1, 2, or 4. Okay. All right, in this case, what is N?
4.
How many patients do you have?
4.
4. 4 trials. And what is the probability of success? We're going to assume success is you get better.
0.8.
0.8. Yeah. Is that part all right? Okay. Part B, scribble out what you have. So scribble, 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 and say, what is the mean and what is the standard deviation? Which I didn't do, but we'll do it on the notes. And this is the thing I actually didn't get to last time, but it was just a formula you were told. You were told that mu was equal to NP. So mu is 4 times 0.8, which is how many? 3.2.
3.2. Doing stuff in your head, man.
I know. And what that's kind of like, this treatment is like 80% effective. So if you do lots of trials before, you expect 80% of the patients to recover, right? Which on average is 3.2 out of every 4. That's 80%. That's where that's coming from. What if you had a 50% success rate? What would this mu come out to be? 2. And then the formula for sigma We'll see if I have it, I think I have it memorized. It was, okay.
Mu times 1 minus.
Wasn't it NP 1 minus P? Is that what it is?
Yes.
Yes, okay. Which NP is actually mu, but yeah, so, yep. So that's square root of 4 times 0.8 times 0.2. And I didn't do that, so could somebody calculate that for me pretty quick here? 0.8, okay. Came out nicely? Wow. And that's how much variability you expect. Like if you did lots of trials of 4, how much variability would you have in recovery rates among your groups of 4, okay? All right, last one that I want to add is my part C. What is the probability that exactly 2 people recover? So P x equals 2. And you don't have to have this memorized, but probability that x equals k was n factorial, right? Over n minus k
P to the
k, 1 minus p to the
Yeah.
n minus k.
Yeah.
You don't have to have that memorized, just put it on your note card and know how to use it. So what goes in for n in this case? 4. K is 2. N minus k is 2. P is 0.8 to the 2, and 1 minus p to the also to the 2. Oh, and sorry, 1 minus p is
No.
1 minus 0.8 or 0.2, excuse me.
It's saying the same thing.
And when I'm grading your quizzes, I'm gonna look and see, did you plug in the numbers correctly? And I'll check and see, did you get the right answer when you punch the buttons in? So don't try any more work than this. This is good enough. Does that make sense? This comes out to be 0.1536. You should verify for yourself that you can make your calculator give you that value. Does that make sense? Like punch the buttons and make it happen, but that's how you use it. You look like you got a question.